Okay, so today I am going to be talking about kernelization lower bounds. Okay, now in the last 10 years or so, there is machinery, uh, exciting developments in area of parameterized complexity, where using which you can show lower bounds for the sizes of the kernels you can get. Okay, so if you recall, you have this. We saw very early on that FPT, the class FPT is the same as problems which are kernelizable, right. So, recall the notion of kernelization. What is kernelization? You are working on a parameterized problem in polynomial time. You want to get an equivalent instance where the size of x prime is some function of k, and k prime is also some function of k. Okay. So, rather than solving the problem, we want to somehow compress the problem, right. So, this, if without this parameterization, this notion of compression is hard, because if you have an NP hard problem, you can't even compress by one bit in polynomial time, because if you can keep doing it and solve it in polynomial time. Parameters gave a way of talking about compression or pre-processing in some sense. So, we saw a lot of problems like vertex cover, feedback vertex set in tournaments, feedback arc set, whole lot of problems, cluster vertex deletion, number of problems where given an input and this parameter, and you are interested in, is there a solution of size k, if k is the solution size, but it could be something else. Then in polynomial time, you are not allowed FPT time, you are only allowed polynomial time. You can compress so that the input size, if input is a graph, then the number of vertices and edges in the graph is k square or k cubed or something like that, some function of k. Right. Yesterday we saw this edge click cover problem, where in polynomial time you can get the number of vertices to be 2 to the k, some function of k, could be exponential. So, very early on in the course, we saw that while kernelization is a way to design FPT algorithm, because once you can kernelize, in this reduced instance you can apply any brute force algorithm and you will get an FPT algorithm. It turns out that any FPT algorithm also is kernelizable. If you can kernelize, you can design an FPT algorithm, but if you have any FPT algorithm through any other method also, there is a simple bookkeeping rule which says that these two notions are actually same, right. Everybody remembers that. This is simple thing, and you should remember, at least that would be a takeaway message of this whole course if you don't even remember this notion. But the size of the kernel for these FPT algorithms could be exponential or doubly exponential, or it could be really bad. Okay. So, if FPT is this class of problems, then a more interesting question is, so FPT is the same as kernelizable. So, in all problems, all of these problems have some kernel, but now you can talk about polynomial size kernel. And you can even break this even more and say order k kernel, k square kernel, and so on. Okay. So, now in the last few years, or what I am going to talk about today, is there is this a notion of some sort of an hardness notion, where you can say that certain problems are not kernelizable to a polynomial size, or even k squares, k cubed, k power 2 minus epsilon size. Now we have some theories to be able to talk about a lower bound for the sizes of the kernels. Okay. So, that is going to be the topic of this lecture. There is a whole chapter in the book on it, and I am going to give to some justice by giving you a flavor of that. We will see some examples. And again, at least in the last few lectures, as we have been seeing, these are all tools. Even if you did not get deep into these things, these tools are already usable for your favorite problems. Okay, right. So the central to this, okay, so there is this notion of distillation. But before that, let's look at an example. This is a standard example, so I might as well do it to see some problem which somehow intuitively is not polykernelizable. So let's look at this k path problem. So your input is some undirected graph G, and the question we are interested in, does G have a path of length k? Okay, is it FPT? Is there a path of length k? Here I mean length at least k, right? Length k if and only if length at least k. Given an undirected graph, I want to know whether there is a path of length k. We have seen it. Yes. So using color coding, this is a popular example for this color coding algorithmic technique. We randomly colored the vertices, then you looked for a colorful path using some dynamic programming, and we argued that it has a good probability of finding a simple path of length k if it is, and it can be de-randomized as well using some hash families. Okay. Another thing, these are things you should know when you, after attending this course. Okay, don't just blink if I ask this question. Okay, it's not just vertex cover we talked about all the time, a whole variety of problems we looked at. So this is FPT. Okay, very standard example is this color coding, for color coding technique. We saw a 2 to the order k algorithm. It can be improved to some c power k for some c smaller than 2. Yeah. So now I am interested. So FPT, so it's kernelizable. There is some kernel. Usually the proof that FPT implies kernelizable gives you a kernel size which is the same as the running time bound. So if you have 2 power k algorithm, then the kernel size will turn out to be 2 power k. So I would be interested in knowing, is there a polynomial kernel for this problem? Polynomial size kernel. Now suppose it has a poly size kernel. This problem. So what does that mean? That you give me a graph G and you ask, is there a path of length k in poly time? So let's say that polynomial size is some k cubed or something for. Okay, so now I have this new graph on G prime, which is some graph where there are some k cube vertices and edges, and you ask, these two are equivalent. There is a path of length k if and only there is a path of length k. Okay. So now suppose I do a disjoint union of some k power 10 such graphs. Okay. So what do I do? So I take such k power 10 instances, and this is my new graph now. Okay. So the new graph is the disjoint union of this large number of instances. And in this new graph, I have the same problem. Is there a path of length k? Okay. Again, it is kernelizable and k is the same k. I am asking for is there a path of length k? The number of instances might have grown, but I am still asking for a path of length k. So, if I apply the kernel algorithm, I will get another G prime of size k cubed, right, such that this graph has a path of length k if and only if this graph has a path of length k. Right? That is what kernelization means, right. I spent polynomial time and all that do not worry about it, but I have compressed it to a graph on some k cubed vertices and edges, this disjoint union, such that this big graph has a path of length k if and only if this graph has a path of length k. But when does this graph have a path of length k? If any one of them, right, it is if and only if, because this is disjoint union. So, this whole graph has a path of length k if and only if there is some component here which is a path of length k, right. But somehow in this, there are k power 10 instances. This compression algorithm somehow, has to remember, suppose there was this one instance which has a path of length k, it is in this compression, because it is an equivalent instance, it should remember that. But this seems too much because you have a lot of instances and you have even forgotten a whole lot of instances. So, somehow in this compression, since the number of vertices in the compressed instance is very small, many instances did not seem to matter in some sense somehow, So, this seems counterintuitive, that you have lost information about these instances of graphs and you have compressed it to a small size, okay. Because this compression should encode which instance has a path of length k, and there are lots of instances. Somehow encoding all of this into this thing seems too much, okay. Now, this is what we are going to model formally and argue. So, the net effect of all of that is that this problem does not have a poly size kernel, okay. Now, we will actually argue this through some formal machinery, and so the starting point of the formal machinery is this notion of distillation, okay. So, we start with some arbitrary language, so L and R, and we say that there is a distillation if there is a polytime algorithm or polytime computable function f which does the following. It takes t instances of L, this is like or let us say t strings of sigma star, that is more, but they have to be somewhat equivalent and so on, I will come back to that, and gives me a string y such that y is in R if and only if there exists an I such that xi is in L. So, basically y is the R function of L, okay. You can think of it as, let me write it big where you can see it. I mean, if this is what I want to get, there is a trivial function which can do the job, right? What is the function? Just write down exclusive OR of this, right? So, take each instance and do an exclusive OR, and if any one of this is true, then that is true, kind of a thing. Right? But I want some more properties such that, okay, first condition that this is an equivalent instance. Y is equivalent to R of the exercise. Length of Y is at most some poly in max of exercise. Okay, so I mean, if you are familiar with complexity theory, you have done some courses. Most of you here have. You know, you'll be able to follow at least the language, but don't worry about it. We'll quickly get to the important part and then start applying it for proving lower bounds. So, this is also called OR distillation, and the running time. So, when I say polynomially computable, okay, so poly time means it is poly in summation xi. So, it takes t instances from this language and produces a y such that this is in the language R if and only if any one of this is in L. Okay. It is sort of like this path problem we said, and you can take the disjoint union as some sort of a composition or a distillation. Now, here are some theorems in complexity theory. If L has an OR distillation to R, then L is in co-NP slash poly. Okay. Again, if you do not know what these terms mean, do not worry about it. Just stay with me for another 10 minutes and we will change the language, maybe longer than 10 minutes. Okay. So, what is this saying? That if L is some language which has such a distillation that there is a, so you can think of it as this is, see, the length of Y is not poly in the sum of this length of the strings, but only in poly in max of the strings. So, in some sense it is a compression. Okay. So, I can compress the OR function somehow. If that happens, then what? So, co-NP, you all know what NP is. A language is an NP if you have a witness for S instance which is polynomially computable, right. Given the witness, there is a non-deterministic Turing machine which will take that string and accept it. Co-NP is complement of NP. So, NP is for S instances, co-NP is for no instances. So, for the no instance of the problem, there is a witness, there is a non-deterministic Turing machine which will actually accept the no instances of the problem, then it is in co-NP. And co-NP slash poly means that it is in co-NP with some help, okay. Ignore what that help is, but something, okay. Okay. And this proof is not very hard, you just need to understand this language, what co-NP means and what this polynomial address is. Otherwise, it is just about 1 page or 1.5 pages and it is there in the book. But here is a corollary of it. If L has an OR distillation to R and L is NP hard, then not just L is in co-NP slash poly, the entire NP is in co-NP slash poly. Okay. So, again this is not very hard, right. How do you show this from the theorem? L, right, because since L is NP hard, by definition any problem in NP you can reduce to this L and then use this co-NP slash poly machine for L, because L has an OR distillation. This theorem tells you that there is a co-NP slash poly machine for that. Use that for your NP problem. So, every problem in NP. So, NP is contained in co-NP is a big open problem. We do not know, right? You know, is it now? This says that is contained in co-NP with some help. Okay, so it is not as dramatic as NP is contained in co-NP, but this is also something which people do not believe. Okay, all you need is that this is something people do not believe, right? Just like P equal to NP is something people do not believe, because a consequence of this is that this polynomial hierarchy collapses to the third level. Which people do not believe. Okay. So, what is the net message? You do not expect an NP hard problem to have an R distillation, because if that happens, something unbelievable happens. Okay. You know, I mean, think of it as like P equal to NP, something which people do not believe. So, some sort of a complexity collapse happens if this happens. So, now so far remember, we did not talk about parameterized problems at all. We are talking only about this unparameterized, Turing machine and languages and so on. So, now we will translate this to parameterized problem, and then we will be set. Okay. So, yeah, okay. So, let us get to okay, we will get to this notion of cross composition. Okay. So, this is all about distillation. It is just that in the unparameterized world, there is a notion of distillation, which just basically compresses the R function, and you do not expect this to happen for NP hard problems. That is it. That is a message out of it. So, what is composition? Or cross composition? So, we have again L is in some language and Q is, this is a parameterized language. Okay, I keep saying language, this is sort of a departure from what you are used to so far in this course, but think of a language as an encoding of a problem. So, you can think of a language as encodings of graphs having a path of length k. Okay, that set is a language. That is it. Okay, so that is the kind of thing we are looking at. So, you can think of a language as a problem, if you like. So, we say that a language L cross composes to Q, which is a parameterized language, if the following happens. Okay, now this is a parameterized language. If again there exists a polytime computable function what does it do? It takes again t instances of L or t strings, and it gives me a y such that y is in it should give me y comma k, right, because it is a parameterized language. What you reduce to is a parameterized language such that y k is in Q if and only if there exists I such that x I is in L. What about length of, now I am just going to say I do not care about the length of y. What do I care about? The parameter k. Now, K I want it to be some poly in max of the excise. Okay. And when we say poly time here, it is poly in same as before summation xi. So, you take t instances of a problem, some language, and we are going to compose it to one string with the parameter. The parameter length is poly in max of the length of any of these strings, and this is an equivalent instance in this sense, and the time you are allowed is poly in xi. Such a thing is called a cross composition. Right now, we are getting into the parameterized world. It looks sort of like the R distillation. The only difference is now I do not care about the length of this y. Y can be very large. It can't be very large because it can only, you are allowed only this much time. So, it cannot be much larger than this, but I do not insist that it is, its length is max of xi. It can be some, does not matter, but the parameter it come up with, that has to be some poly in this max of xi. Right? It is like now, so for example, we can talk about k t instances of Hamiltonian path instance. So, I can have G1, G2. So, my language may be all graphs having Hamiltonian paths, graphs on n vertices having Hamiltonian path. So, now I take t instances, t graphs, and produce my y, which is the disjoint union. Right, this is my y, and my k is going to be n, number of vertices in the graph. All right. So, now look at it. The length of this instance is very large, it is the sum of the instances, right, but I did not specify anything about y. But the parameter is poly in max of length. So, I am just going to give n. Now, this is an equivalent instance because this disjoint union has a path of length n. N is the number of vertices in each of these graphs, if and only if any one of this has a Hamiltonian path, right. So, this is like a cross composition. So, now you know what next should be, right. Now, what we are going to say is that if you have an R cross composition to a problem which is NP hard and it is poly kernelizable, I can turn it into a cross R distillation, and that does not happen for NP hard problem. So, you do not expect a poly kernelization. Okay. So, let me write the theorem and then we are ready to use that. So, before that, let us just generalize this notion of kernelization, because the theorem which we are going to prove is useful for even for some larger class of algorithms. So, let us talk about polynomial compression. So, what is it? We take a parameterized problem q comma k, okay, and it will not be a bad idea to just think of it as a graph and some integer k. You are allowed poly time, and you get to another language L. So, let us call this. So, this is a, yeah. So, this is okay. Now, I should just talk about a parameterized language Q cross N to a parameterized language L cross N in poly time, such that you take an x comma k, you get an x prime comma k prime, such that x prime length is some function of k, right, x prime and also k prime, and of course, these instances are equivalent. So, x prime k prime is in L if and only if x k is in Q. Okay, so, yeah, two parameterized languages. So, you take an instance and a parameter, it's parameterized instance. In polynomial time, you get an x prime k prime, where these are functions of this parameter, and it's an equivalent instance. In what sense this is different from kernelization? Yeah, but that, I mean, our kernelization, what is the definition of kernelization? This is exactly that. What are you doing in kernel? No. In kernelization, for example, in vertex cover, when you go and reduce, you have a new parameter because you have picked up some vertices and so on. Yeah, x prime, comma k prime, they are all functions of k. And what's the L? This is a different problem. Okay, in kernelization, you insist that you start with a vertex cover. In polynomial time, you get a vertex cover problem. Here, I am happy to reduce to some other problem, right. So, that is a difference. So, a kernelization is also a compression, okay, but compression is more general. Okay, and this is very useful. Sometimes, maybe we start with the dominating set problem, and then we do some kernelization, we get some colored graph where you need to do something. Remember, if you have done this exercise on red, blue, green, or whatever G5 graphs you want to do dominating set, you will do some coloring, and then you do some reduction in polynomial time. Finally, you do not have the original dominating set. You change the problem a little bit, and it's convenient sometimes. So, this is what this compression is. Okay. Now, if Q is NP hard, which is what we usually work on, and L is in NP. Okay. So, like I said, ideally I want to start with the problem, do some pre-processing and get to compressed instance of the same problem, but I am saying compression may actually get you to some other problem. Okay. But in this case, if you start with an NP hard problem, which is almost always the case, and if L is an NP, which is also almost always the case, then what? Then you can actually get kernelization rather than compression. How? So, reduce that to Q, right. What do I want kernelization? I want an instance of Q. Since L is an NP and Q is NP hard, there is a polynomial time reduction from L to Q. But what happens to the sizes and the parameters and stuff? Not a problem, because x prime is already just a function of k. All these are functions of k. You do some polynomial time reduction, you get another function of k. Okay. So, this is a function of k, the parameter will be a function of k, and you can get there. Okay. So, in this case, you can actually start from Q and get to Q. However, sometimes it is convenient to talk about compression, because suppose I care about k square kernel or k square compression or k power 5 compression, and I am trying to fight to show lower bound for that. If I really want kernelization, when you go from here to here, you might just blow it up. It might become k power 10, because this polytime algorithm might just do something, right. So, and this is a reduction which is not in my control. If I am just going to, if I am create a reduction and do it by hand, then I will have a control. But if I say, this is NP hard, this is NP, so I can use the standard poly time reduction, you don't know what the standard poly time reduction will do to the parameters. So, sometimes we will leave it at compression and it's useful. And in fact, there are problems for which there are some polynomial compression, but there is no polynomial kernelization. Or no, if this happens, then polynomial compression will immediately give you polynomial kernelization, because you just do this. But there are problems for which you may have a k cubed compression, but you do not have a k cubed kernelization. Okay. So, when you talk about such finer bounds, the differences happen. Okay. So, now here is the big theorem, and then we are ready to move on. Yeah. So, if L cross composes to Q, right, is L is some, it is not even a parameterized language, right. When we started off, remember, L is not a parameterized language, need not be a parameterized language. Okay. You can just talk about some optimization problem, something, SAT, whatever, right, minimum dominating set, whatever. Then we cross compose to a parameterized language. So, if L cross composes to Q and L is NP hard and Q has a polynomial compression, then this happens. Again, this is not hard given the way we built things. So, all we have to do is to, from, so what is this saying? I start with L, well, cross composition means some t instances of the language, and I get somehow I have compressed it to some y comma k of a different language, and this has a polynomial compression, and if L is NP hard, then it makes whole NP contained in co-NP slash poly, and the idea is to actually get a R distillation from L and then use the previous theorem we have shown. So, then you do not expect this, because this collapse is unlikely. So, now if I want to show that a problem does not have a polynomial compression or polynomial kernelization, what do I have to show? So, let me write that, and that is going to be our template, and we will start using it, right, to show that a problem, a parameterized problem, has no polykernel under this assumption. Right. Always when we talk about no means it, no polytime algorithm, no polykernel, have some assumptions. To show this, what do I have to show? So, that is a cross composition from an NP hard problem to this problem. Okay, by this theorem, right, because if there is a cross composition from some NP hard problem to Q, then from this theorem Q cannot have a polynomial compression, because if Q has a polynomial compression, something bad happens. Okay. So, now this is it, we now really have to. So, often what is the NP hard problem you will choose, it might turn out to be the same problem Q. And remember, what is cross composition? It takes some t instances and produces a string, t instance of some NP hard problem produces a string with this parameter, where this parameter is bounded by max of this. So, let us get on with some examples. Now, there is some technicality which I am just omitting. How are these t instances, right? Start with some t instances and you are going to compose it. Typically, these t instances are going to be, graphs on n vertices and m edges, and some k is my parameter or something like that. Okay. If I am talking about graph problem, I might be talking about some other problem. So, there is a notion of equivalence relation, and you pick something from equivalence class and so on. It is explained in the book, and I am going to omit that, because that is just a side issue. It is important when you actually get into these proofs of this theorem, that plays a role, it is important, but the way we apply it, we do not have to worry about it. Okay, so, let us start with the k path problem. So, I want to show that k path problem is given a graph, is there a path of length k. Showing that there is no polynomial compression is even stronger than saying there is no polynomial kernel, right? Because kernelization is a little more restricted. Compression is a little free, you can reduce to some other problem, but we are going to say that there is no polynomial compression for k path, and we already saw it more or less, that the example I started off with is now formally captured through all this machinery of cross composition. So, what do I have to do? So, somebody gives me t in. So, what is the NP hard problem I am going to choose? The same k path problem. Given an input g on n vertices and a parameter k, is there a path of length k? This is an NP hard problem, right? So, my L, so I am going to say NP hard problem L. So, what is my L? This is just the k path problem itself. So, I take t. So, what is the cross composition? I am going to give you a cross composition. I take t instances of this g1, g2, g3, where in each one I am interested in a k path of length k. Now, k is the same and n is the same, we will assume that, and this is where this relation, equivalence relation comes into picture, but do not worry about it. So, suppose I have t instances of graphs in which I am interested in checking in each one of them whether there is a path of length k. My cross composition will take all this and it has to produce some y and k. So, what is this y? It is this disjoint union, right. I am interested in k here, and this disjoint union is the same and the same k. Okay. And this has a path of length k if and only if there exists an I such that that is a path of length k. It is trivial here, and what are other properties? I spent polynomial in the sum of these instances time, and the parameter k is max of the lengths of these instances. Okay. Very rarely you are lucky to get such a nice simple cross composition. Okay. It is also useful to know, because you did not learn much from this example, right. When you get to some, let us get to some little involved example and you will learn. Okay. Let us get to this, more non-trivial. So, let us look at this problem of set splitting. So, what is the input? You have a universe and a family is what fixed? T fixed? No, T is something arbitrary. Take any T instances. Yeah, I did not assume anything about the number of instances here. The important thing is this parameter cannot be the sum of the parameters or the length, instance length. This is the crucial constraint. The parameter has to be the max of this. Because for example, let us say something like vertex cover. What happens if I do this disjoint union, right? It has to be the sum, because I will say there is this, k, this graph, there is a k and I am looking at this. Then I suppose I simply take the disjoint union, then this disjoint union has a vertex cover of size at most, I do not know, can you say something? Yeah. So, let us call this G prime. So, G prime has a vertex cover of size at most T times k. T is the number of instances, if and only if there exists an GI such that has. Is that true? No, I do not think even that is true. No, this is not true. Yeah. So, it is like an AND composition. First of all, so there is this notion of AND composition about which I am not going to talk about. That is also useful sometimes, and that many of this theory go through for AND composition also. Yeah, if and only if for all GI. What would be an example? So, what would be an example where the natural parameter is the sum? Yeah, something like in fact, the same reduction goes through for even for something like clique, that this disjoint union has a clique of size k, if and only if there exists a GI for which there is a clique of size k, right. If there is somebody who has clique size k, then this guy will have, and if this has a clique of size k, there is some I. So, what have we shown about clique? If this happens, that clique has no polykernel is what we argued. Is that an interesting result? Yeah, the same thing goes through for clique, right. So, as a consequence, k clique has no polykernel. Is that an interesting result? Why not? So, it has no kernel at all, right, because FET and kernelizable are same, right. Since click is outside. So, it is correct. I mean, it has to be consistent. It is correct. There is no polykernel is correct. This reduction tells you that there is no polykernel, but we knew it already from the fact that it is W1 hard, that forget polykernel, it does not have even exponential or triply exponential kernel, because it is not FPT. When FPT and kernelizable are same. Okay. So, but yeah, click also has this property. But you can think of examples where the natural parameter is the sum, and that is not allowed here. You really want a max of this, but T is arbitrary. Okay, so set splitting. What is the question? Is there a subset X of U such that X intersection F is non-empty and and X bar intersection F is also non-empty for all F in the family. If I just said this is the heating set problem, exactly the heating set problem, that I want to intersect every set. But now what I am saying is, I want to come up with the set such that for any set it should contain some element which is there, and it should contain some element which is not there. Okay, so I want to split every set. Our parameter for this reduction is going to be n, not our usual solution size, but we are going to take our parameter as the size of the universe. Okay. Is the problem FPT? Again, it's sort of counterintuitive. We are used to solution size as a parameter, but when n is a parameter, you try all subsets of my universe and check with intersecting with every family, every set in the family, right? So, it is 2 power n times the size of F. So, it is FPT, but I want to argue that you can't compress particularly the family. You can't come up with some reduction rules so that your family becomes polynomial in n family size. Okay, so that is what I want, right? That is what compression means, that you want to compress my input size so that the size of the family, which could be exponential in n, that you can't come up with some reduction rule so that now the size becomes polynomial in n. Okay. And the way I am going to do it is that it cross composes with itself. So, take the set splitting problem, t instances of them, we are going to come up with one instance such that there is a splitting set for this reduced instance, if and only if there is a splitting set for any one of them. There is okay. So, I missed one important thing. What is the thing I missed? I said yk. Okay, this is a very useful thing. In fact, I am going to use it. What did we say about? So, I take in the cross composition x1 xt gets reduced to some yk such that this y is encoding the r of this, and I wanted k to be what? Is poly in max of xi. Now, I want some leeway now plus log of t number of instances. Okay. It turns out this entire proof of NP, contained in co-NP slash poly goes through even with, if you allow your length of this reduced instances to be max of xi plus polynomial in log of the number of instances. Okay, you do not allow polynomial in the sum of the lengths, but I allow some log t leeway, and this log t leeway is very good. You know why? Because what am I trying to do? So, I have this somehow x1 to xt, and I want to get y. This y should encode all of these variables, right. So, I will, so some solution exists here if and only if there is some of I for which such a solution exists here, right. So, this I will use this log t bits to encode which of the I that is. So, okay. So, somehow that is going to be useful. Okay. I mean it is very high level, it is it's not at all clear how I will do it, but I am going to use this log t bits to encode which I that is. Okay. So, let me just give a high level overview of how this compression goes or cross composition. So, we start with t instances. So, just to make sure that log t is an integer, let us make t to be a power of 2. Okay. If necessary, just duplicate some of these instances, not duplicate, make copies of it, so that you have a power of 2 many instances. And we will assume that all the universes are the same, all of them, all the sets are over the same universe of size n. Now, I want a subset of U that splits family, and I want to somehow encode the fact that R of this. Yeah. So, again I will not do the gory details of the proof, but I just want you to understand this encoding idea. So, I will just go to so let us actually call it U0 F0 just to use this binary encoding business. Yeah, t minus 1. So, the universe is same. So, let us remove the universe out, they have the same n elements, all of them are same. Now, I take the sets here, right. So, this sets in F naught contain some A1, A2, some number of sets here in this family. What I am going to do is that I am going to add some new variable log t many new variables, and my encoding is going to be, so let us call so let S be log t, and I am going to write some x0, x1, x s minus 1 or my okay x0 0 right, and then x0 1, x1 1. These are some 2s many extra elements of my universe. Okay. I have my original universe that are some n elements, right. Now, I am going to create some more elements of my universe, that is like 2 log t extra elements. So, now my parameter just goes from n to n plus 2 log t, which is allowed, because I am allowed polynomial in log t. So, okay. So, now for every set in this family, I am going to write x0 0, x1 0, x s minus 1 0. Okay, and okay, so this is my A1, call it A1 0 or A1 B and A1 1 minus B. I will tell you what B is, and I similarly create A2 B, A2 1 minus B and so on. So, for every set in my family, I am attaching some new elements which sort of doing my encoding. Okay. It is a log bit encoding. Now, since so I look at the binary representation of this, because ultimately this binary representation is going to tell me which set from which my splitting happens when I compress into y, right. So, 0 0 0 0 is my binary representation. So, A1 B will have x 0 with 0, x 1 with 0, everything with 0, and 1 minus B is going to have all of this as 1. So, for every set in this family, I am going to attach these elements. Now, I come here, right, is this clear? So, now I have created a new family of sets for these guys. Now, I come here, and for every set in this family, what am I going to do? I am going to attach my A1 B here is look at the binary representation of this thing, and in the top I write down that binary representation. So, this is 0 0 0. So, right. So, for example, this binary representation is 0 0 0 0 1. So, it will have x 0 0, x 1 0, x s minus 1 alone will have 1, and this will have the flip of that. Okay. So, for every set in, so in general for every set in some Fi, I go there, write the binary representation of I in s bits, and then write x 0 b 0, x 0 x 1 b 1, x 2 whatever that bit is, and write that set, and that is my y. Y is this huge, the universe with expanded with this to so many elements, some 2 log t elements, plus this entire family of sets, right, this union of all these families with these extra elements added. Okay. And I will add a few more sets. What is a few more sets I need to add? You want to split, right. So, I will add x 0 0 and x 0 1, which means the solution I am going to pick will pick exactly one of this. The solution I am going to pick, because it should intersect this and not intersect with something. So, it will pick exactly one of this. So, similarly, I will I expanded the universe by adding these elements, and I expanded the family in the following way. For every set in Fi, I added this corresponding, for every set I added these elements. Originals? No. The original sets are attached with these. The original sets are not there anymore. With the original sets, I have added some extra elements based on the binary encoding, and that is my new family. Okay. And you can see that it actually satisfies time and space and so on, because my new parameter, the n has gone from n to n plus 2 log t, that is the parameter. I have spent time proportional to polynomial in the sum. Now, I claim that there is a subset x that splits some family if and only if there is another subset here, the size will increase by some log t. Okay. Okay. So, the claim is there exists an X that splits some UI Fi of size, say some L, if and only if there exists an X of size L plus S that splits my Y, right, which is this big union. Okay. So, here is a sort of a one line proof, because to understand what this encoding is happening. So, let us do the one, usually the forward direction. Suppose some UI Fi is split by some set, okay, some X was splitting all elements of some set. Okay. So, let me draw a picture here. So, you have U1 F1, U2 F2, let us say here is this thing. So, remember this had a lot of sets, right, some A1, A2, AL. So, there is some subset of my original universe that actually split every AI here. Okay. Good. Now, I want to come up with something which will split this union of the Fi's with its attached new elements, right. Now, I really do not have to suppose. So, what I will do is I will take that set X and add some more elements, and I will argue that it splits every set here. Okay. Now, I do not have to worry about these sets, because the original X itself splits that. And when once I am going to add some more elements, it will split all of this. So, I can just ignore this thing, right. But I am going to use this binary representation of this L, whatever that thing. So, what I will do is basically I take my original X and union my X0 of B 0 L, X1 B1 L. What do I mean by this? Write L in binary. L is this guy whose original universe is splitting it. Write L in binary, and that is this B0 B1 to Bs minus 1. Okay. Take the corresponding Xi's and attach to it, and I want to argue that splits every set. About these guys I do not have to worry about, right. But if you go to every other Fi, they all, each AI in that set has one of these guys, but they will differ. The binary bit will differ in one of these positions, okay, both in A1 and A0 and A1. So, you can use that to get something which intersects this and not intersecting that the particular bit that differs will be your candidate. Okay. I mean, it requires some, the thing about the write up in the book is it's very notation heavy. I mean, already I have introduced a lot of notation, but it's much more than that, and I guess it can't avoid it, but to understand what's happening. Now, to go to converse, suppose in my entire this new thing there is some set that splits all sets here, right, some subset of the universe. Clearly, it splits each one of these guys. So, there must be some X0, some X1, some X2, everything will be there. Take that, and that will actually give you a binary encoding, and you can argue back that that particular Fi will be split, because in that Fi the additional things are not helping me, because they are identical to my this thing. So, the original guys must split them. So, you will argue that the original set, there is a set subset of the original universe that splits that particular a particular UIFI. Yeah, I mean, clearly I did not tell you all the details, it requires work, but you understand this, how we are using this log polynomial in log t bits to do this nice encoding of the selectors, right. And that is what these S elements are doing the job. Okay. So, then I will just add 2 more examples, I will spend 5 minutes each on them. No. So, one example I am going to completely skip. Now, so we have seen cross composition, right. What is cross composition? Take the R of it, compress it to your problem instance, make sure that parameter is the max of the sizes. That is all you have to do, right. And somehow it has to encode the R function. So, in one example, just the disjoint union was good enough. In other example, we carefully used these log t bits to encode this, to go from here to here and go back there. Now, if I want to show something is NP hard, what do? You are not going to always reduce from SAT. You pick another NP hard problem and reduce to your problem, right. So, that machinery also happens here. So, you do not necessarily have to design a cross composition all the time to show us there is no polykernel. So, what do? So, I have given 2 examples. So, method 1 is cross composition. Method 2 is called polynomial parameter transformation. I think that is the abbreviation. It is called PPT reduction. Now, you can guess what is going to happen, right. So, you want to show that your problem QK has no polykernel under whatever that assumption is. So, what do? Somebody has already shown that set splitting has no polykernel under this parameter, which is the universe size. So, you start from set splitting, size of the universe is the parameter. You spend poly time because we are all in poly time algorithm world. What else should happen? Exactly, that is it. Just make sure that this parameter is a polynomial in this. I mean, when we talk about FPT reduction, we just want this parameter to be a function of this parameter. I do not care what function, but in PPT reduction, you just want K to be poly in size of this universe, right, whatever, or your favorite no polykernel problem. In poly time you reduce to this, just make sure that K has. So, there are no polykernel results where you want to show this problem. Sometimes coming up with cross composition may be very hard, but you can often there are a couple of papers where you introduce some intermediate problem for which cross composition is easy, and then reduce from there in polynomial time with this polynomial parameter preserving reduction, and you can show there is no polykernel. Okay. So, this is a method and there is some couple of examples in the book on how to do this. Okay. These are very useful and these are just tools, right. I mean, you know these proofs are not very hard, you can go through them, but if you do not want to know about the theory, complexity theory aspects of it, you can still use these tools. All you are trying to do is compress R of these several instances with some constraints on the reduction. Okay. Finally, all this is fine, we have been able to show a lot of problems for which are FPT and we could show that there is no polykernel. Now, what about problems for which there is polykernel and we want to know whether the kernel size we have obtained is optimal, right? And turns out there is some machinery to do it. And that takes us to this notion of weak composition. So, what you do is again you take these t instances of some problem and you reduce to y parameter k. You are allowed poly in summation xi time. Now, I am going to allow k to be poly in max of xi and some t power delta, where delta is less than 1, or let us say t power 1 by d, where d is greater than 1. Okay. Earlier I allowed log t here. Now, I am going to say some little of t, or actually even no, t power 1 over d. I mean log t is little of t power 1 over d for any constant d. Okay. So, now, so have we made this reduction easier or harder now? It is easier, right, because now I am going to give you little more leeway on your parameter now. You know, do not tighten yourself to get something poly in log, but actually you can do some t power 1 over d, and that is why it is called weak composition. Okay. It is not the strong composition. Now, if such thing happens for an NP hard problem, right. So, this is my Q. If Q has a weak composition, so let us say weak D composition to refer to this D, and has a t power d minus epsilon kernel or k power d minus epsilon kernel, then NP is contained in co-NP slash poly. Okay, so we really didn't depart too much from this idea of cross composition. We allowed a little more leeway. Now, you can say that by allowing this, if you have such a composition and if this is D, then one can show that you do not have a k power d minus epsilon kernel. So, this is weaker result, right, because okay, the way you look at it, for a problem for which I do not even know whether there is polykernel, this is a weak result, because I am just, this says, oh, there is no k power 3 kernel, that is all I might say. There is no k power 3 minus epsilon kernel, it is sort of a weak result, because I have allowed the leeway to do. So, ideally I would like to say there is no polykernel at all, but I am allowed to say k power 3 minus. But for a problem for which you already know there is a polykernel, then this gives you a tight result. And so, for example, it is known that vertex cover FES, or in fact even have no order k power 2 minus epsilon kernel, unless, right, conditions apply. Yeah. And the way you show is give a t square, a parameter which is poly in max xi and t square, sorry, square root of t, yeah, square root of t, right. Instead of log t, I am going to allow myself square root of t. That is a very beautiful result. I do not think I have time. It's, it's doable in 15 minutes, but that there is a way to reduce multicolored biclick problem to vertex cover, maintaining that this parameter becomes square root of t. I take t instances and I can embed it. So, this is all about embedding the R of multiple instances into a small space, right. So, this is a very nice beautiful theorem. I mean, you can look at the proof in the book, which tells you that you can embed multicolored biclick problem into vertex cover with this d being 2, which will imply that you do not have k power 2 minus epsilon. Then vertex cover to FES, there is a standard simple reduction which preserves k to k. So, you have this for FES also, and in general for a d heating set, it tells you that you can't get d minus epsilon kernel. And there are lots of hazy things here I did not get into. One is about this equivalence relation of how these t instances are related. What do you mean by I look at the t instances are graphs on n vertices with the parameter k? I mean, are they arbitrary t instances? And the other thing is, when I say this kernel, this is the bound on the number of edges or the number of hyper edges here, but the number of vertices can be smaller. Okay, and how low can that be, and is there a way to show some lower bounds on that? We do not know. Yeah, okay, I think I will stop. So, that just gives you a flavor of, again, some simple combinatorial or complexity theoretic tool to show. So, now given a parameterized problem, you know whether it how to show its FPT, you have learnt a lot of tools, you can kernelize it, you can show its W hat, and you can also show that if it is FPT, whether it has a polykernel or not. There is enough to explore about a particular problem.